So we are starting on Unit 6 bonding. Some people wanted my videos back, so I'm basically going to do a hybrid. I'm going to go through my notes really quick so you can take them, and then I'm going to go through them again in class in way more detail. So take your notes, you have them ready, so you won't have to be taking notes while I'm doing my in-class lecture. So Unit 6 bonding is again in your workbook. You should be reviewing your workbook and using it as a resource. So if you don't understand how I'm explaining it, you can also find it in your workbook. I will also urge you to stay with me after class. If you don't understand something, I have a half an hour after every single class to work with you. Okay? So bonding, atoms are bonding through electron interaction, okay? And why do they do this? They want to achieve a lower state. We have two kinds of bonds. We have ionic bonds between a metal and a non-metal, and here they're giving up and they're taking electrons. So here's my sodium. It has one valence electron. My chlorine has 7. Remember, we want to form a full shell, so chlorine steals this electron from sodium. Why? Because it's more electronegative. That trend, electronegativity, dictates this, and it has a greater pull on those electrons, so it pulls it closer. Okay, so then we form a sodium plus ion and a chlorine negative anion. So cation are positive, and anions are negative, a negative ion. And then what happens is they click together like magnets. This is called electrostatic interaction. If our electronegativity differences aren't that great, we can share the electrons because they're not ripping it or pulling that electron off, okay? They're gonna share them, like hydrogen and oxygen, and we make water, okay? So one line here equals those 2 electrons. Hydrogen has an electron, it bonds with this from oxygen. And we're gonna go through these dots in more detail. And they bond through sharing of electrons versus stealing and clicking together like a magnet, okay? Ionic compounds are called formula units. Why? Because they don't make a molecule like a covalent. So a covalent has this very distinct molecule, and when I put that in water, these molecules stay together. Where sodium and chlorine just keep clicking together on and form this crystal lattice structure. And when I put this in water, they split up into ions, sodium and chlorine. And that is why ionics can conduct electricity, because they have charges in the water. This does not have a real charge. It has partial charges that we'll talk about in a second. So there are 2 types of covalent, or the sharing molecules. Okay, we have polar and nonpolar. Nonpolar has even electron distribution. That means the electronegativity are so similar that they're not pulling the electrons towards one side. So remember, electronegativity dictates this trend, and our trend goes this way. More electronegative is up here. Okay, so if I take this little cutout, I look at boron, we have these electronegativity values. That's from a chart. They would be given to you. And I get more electronegative as I go over here. As a matter of fact, fluorine is the most electronegative atom on the chart. Oddly, remember, hydrogen is a nonmetal, so it kind of squeaks in between boron and carbon with electronegativity value of 2.1. So we want to think of this electronegativity as a pull, right? It's attracting those electrons. So boron has a 2.0 electronegativity value, and fluorine has 4.1. So fluorine's pulling, attracting those electrons harder. So we write this arrow, and this arrow is called a dipole. Okay, so when I pull all these electrons over here, I get a partial negative charge. Why? Because my electrons are hanging out around the fluorine. Boron has a plus charge there, okay, because it pulled those electrons away from boron, and when I lose electrons, I'm not completely losing them, but when they're moving away, I get more of a positive charge over here. So this arrow shows the 2 different sides of the charge. And those are called poles, okay? We have a positive pole and a negative pole. And you've probably seen this with magnets. And we denote the positive and negative pole with this delta sign. That means a partial charge, okay? So how are we going to figure this out? Well, we have this bond continuum and we have nonpolar over here all the way to ionic, and we are going to use our electronegativity values and we are going to find the difference between them. My line is absolute value. So if I have two oxygens together, they both are pulling evenly. So who wins in that tug of war? Neither one of them. They're identical. So 3.5 minus 3.5 equals 0, and this is non-polar, okay? So if we look over here, carbon and oxygen are not the same atom. That means they have different electronegativity values, and one's going to pull harder. If I look at my trend, oxygen is more to the right. It has more protons. It's going to pull harder, so it pulls these electrons over here, and I have a partial negative value here and a partial positive there. If I subtract the values, I get an electronegativity value of 1, and that's going to mean something in just a second. Then I go all the way to ionics. So sodium has a value of 0.9, and this is a 0.9. That's not a 1. These are my absolute values. Minus 3 is absolute value of 2.8, okay? And the chlorine pulls so hard, I actually get fully charged molecules there, or excuse me, fully charged ions there, okay? So what do these electronegativity differences mean? Well, first of all, they come from a chart. That's in page 111 on your workbook. And if I have a difference of 0 to 0.3, I have a nonpolar molecule. 0.4 to 1.69, that means I have a polar molecule. And see right here, I'm at my polar covalent. I have a 1 there, and 1.7 and above means it will be ionic. Okay?